This module will show you how to conduct a one-way analysis of variance, also called an Anova, in SPSS. If you want to follow using the dataset, please open the module 16 _ Anova dataset to follow on. An Anova is a test of independence between the one independent variable and the group factor. It is an extension of the independent t-test as the categorical factor has more than two groups. One reason why we may run an Anova rather than multiple t-tests is the Anova test minimises the type 1 error that would occur by rerunning the t-test over and over again. There are two main types of Anova. There's a one-way Anova and a two-way Anova. However, this module will only explore the one-way Anova option. So the Anova compares the variance between different groups and the variability within each of the groups. An Anova reports the F statistic, which tells you whether there are differences in the means between the groups. And then a post hoc test will tell you where those differences between the groups actually lie. Anovas have several key assumptions that we'll need to test first before we can proceed with the Anova. First, we need to have a look at our variables. So we need to ensure that we have one dependent variable and one independent variable, which is categorical with 3 or more groups. So for example, if we are wanting to know if there's a difference in exam score based on the different style of teaching, exam is our dependent outcome variable, and as you can see here, it is a scale continuous variable. We then have group, and group is indicating the type of teaching style used. And if we come up to the top here and click, it will actually convert to see how it's coded. So we've got punish, we've got indifferent, and we've got reward as our 3 groups. So we can confirm our first assumption, that our variables are correctly coded. Our next assumption, assumption 2, we need to understand and make sure that participants that are in one group cannot also be in a second group. And here we can see that if they were coded in group 1, it's a different ID number as we scroll down and have a look for group 2 or group 3. So therefore, this means that a student can only receive one form of teaching style. Our third assumption for an Anova is the parametric assumptions. So we need to have a normally distributed dependent variable with no significant outliers. And we also need to have homogeneity of variance between groups. So first of all, let's check normality. And there is another module that will go into this in further detail if required. So for normality, this assesses the assumption that the mean value will be normally, for the dependent variable, will be normally distributed. To do this, we come up to analyze, come down to descriptive statistics, and we come down to explore. We move exam mark across into the dependent list. We select plots. Under box plots, we want our factor levels together. We want to select histogram, remove stem and leaf unless you want that one in there. And we need to left click for normality plots with tests. We then click continue and we click, in this case, OK. Our output screen should then pop up and you'll notice this first bit of syntax coding saying what it's doing. And we can see down the bottom that it's currently running this process. Our first screen that appears is the case processing summary. So it tells us that there's 30 people in the sample and that 100% were valid with no cases that are missing. When we have a look at our descriptives table, one of the things that we want to look at is the skewness and the kurtosis, and we want to make sure that these aren't too extreme for their values. The next part that we're looking at is the tests of normality table. We're using the Shapiro-Wilk test statistic, and we need this number here to be greater than 0.05 for us to assume that exam mark is normally distributed. So in this case, as the number is 0.75, this is greater than 0.05. So we can say that exam mark is normally distributed. In your write-up, you would be reporting this statistic value, 0.937, and you'd be reporting this sig value, which is your p-value. So p equals 0.075. The histogram can also assist with deciding if the data is normally distributed. We'd be looking for a bell-shaped curve to be coming over the top of this. In this case, this isn't the perfect example, but we can see it starts with lower values, peaking up in the middle, and then coming back down again. With the small sample size, this is potentially why this shape is less than desirable. Next, we want to come down to our normal QQ plot, where there's a straight line coming up here on the diagonal, and then we have all our points plotted. With a normal QQ plot, this is plotting the expected values against the observed values. We can say that normality is assumed when the values are as close to this line as possible. In this case, they are coming away from the line a little bit. However, they are not extreme values. So in this case, we can say that we assume normality. Now that we've checked all three assumptions, so our variables are correct, such as we have a dependent variable that is continuous and an independent variable that is categorical with 3 or more levels. And our assumption 2, that participants only belong to one group, and assumption 3, that we have normality. We can now proceed to complete our Anova. We're going to come up to Analyze, Compare Means, and we come across to our one-way Anova button at the bottom. We're going to move our exam mark into our dependent list, being our dependent variable, and we move our independent variable, which is type of teaching method, into our factor box. Under post hoc, we're going to select a Bonferroni post hoc if equal variances are assumed. So this is if homogeneity is assumed. We want it to do a Bonferroni post hoc. And if equal variances are not assumed, we're going to ask for a Games-Howe post hoc. So this means instead of having to test homogeneity prior to running the test, we can actually test it as part of the one-way Anova. And this means that we can proceed with reporting whether we have equal variances or not. And then click Continue. We then come down to Options, and we'd like Descriptive, Homogeneity of Variance, Brown-Forsyth, Welch, Means Plot. And we don't have any missing values, so we don't need to be concerned, but otherwise keep it as the default, which is analysis by analysis, and click Continue. We then click OK, and we have our output. So the first table is giving us our descriptive. So we can see there's 10 people per group. Their mean exam mark score, so Punish had a 50, Indifferent had 56, and Reward had 65.4. So already we can see that visually there appears to be some kind of difference between the three groups, with punish having the lowest score and reward having the highest score. This also gives you your confidence interval for the means, as well as your range here, so your minimum and maximum score. Our next table gives us our homogeneity of variances. So we're using this based on mean. So our Levine statistic is 2.569, which you'd report in your write-up, and your sig is your p-value. So a score greater than 0.05 indicates whether or not there is homogeneity of variance assumed. This score being greater than 0.05 indicates there is homogeneity of variance, therefore there is equal variance between the groups, and therefore we can continue with the standard ANOVA. So with the standard ANOVA, we look at this first table here. If we didn't proceed with the standard ANOVA, so if homogeneity of variance was not assumed, i.e. our p-value was less than 0.05, we would need to come down and use either Welch or Brown-Forsyth. And that's when we also use our Games-Howard post hoc. However, that is not the case, but we will have all these tables presented for us to look at. So knowing that our p-value is greater than 0.05, and as I said previously, therefore homogeneity of variance is assumed, we proceed with looking at the ANOVA table. We have our F statistic of 21.008 that you would report. This is your degrees of freedom 2, which you'd also report in your write-up. And sig is our p-value, which is 0.000. This means that p, you'd write less than 0.001, therefore there is a significant difference between groups. Since there is a significant difference between groups identified, we can now proceed to the post hoc to find out between which actual groups is there a significant difference. So we scroll down to our post hoc test. Because homogeneity of variance was assumed, we're going to be looking at Bonferroni, so this top section of the table here. And we're wanting to look at our sig scores here. So this is our p-value. So we can see that between punish and indifferent, there was no significant difference. However, between punish and reward, there was a significant difference because that value is less than 0.05. Now it's a two-way table, so we've got indifferent and punish now repeated, but we can see that indifferent and reward is 0.002. So therefore there are identified some significant differences between the actual groups. And when we have a look at the means plot, this further makes sense. We're looking at punish being down the bottom, indifferent and reward. So to report your findings, first of all, you would report the overall group difference, which is from your ANOVA table. Then, because there is a significant difference, you would then report your post hoc findings from that Bonferroni post hoc section, and you'd be stating which post hoc test was used. So for example, you may say something like, there was a significant group difference in exam performance based on teaching style, and you'd insert your values there. Bonferroni post hoc analysis indicated on average, reward had a greater mean exam score, and you'd insert the mean and standard deviation for that reward score, than punish, and indifferent. There was no significant difference in mean exam score between indifferent and punish teaching styles.